Hello, everyone. My name is Karampelas. I am a postdoc at Northumbria University, UK, also supported by an FWO fellowship and KU Leuven, Belgium. And today I would like to talk to you about a work in progress regarding oscillatory reconnection of a 2D magnetic X-point. By oscillatory reconnection, I am referring to periodic changes in magnetic connectivity of an X-point. This has been proposed as a possible mechanism behind the generation of quasi-periodic jets, as well as quasi-periodic pulsations in the solar atmosphere. The aim of this study is to expand an older work done by McLaughlin et al. 2009, introducing a parameter study for setups with different base temperatures. We also wanted to include new additional physical effects like isotropic thermal conduction and see how they affect the evolution of oscillatory reconnection. To do this, we solve the 2D resistive MHD equations using the Pluto code. For our setup, we are employing coronal conditions for density and the magnetic field, and we have a base temperature range going from 1 Kelvin to 1 megakelvin. On the right, you can see our basic magnetic X-point configuration, which we choose to perturb using a circular velocity pulse perpendicular to the magnetic field lines. Once the X-point is perturbed, we can track the magnetic field lines as well as the generated current sheets and prove that indeed our setups have the phenomenon of oscillatory reconnection taking place. By focusing on the X-point, we can track the value for the JZ current density over time and thus construct a profile for each simulation that we have run for our parameter study. All these profiles together are shown in figure 1, where it is obvious that not only do we have an oscillatory behavior of these profiles, but also we have a decaying oscillatory behavior over time. Indeed, as it was already found by McLaughlin et al. In 2009 for a case with cold plasma, our profiles tend to go to a positive asymptotic JZ value, as it is obvious, especially for the hotter plasma cases of 1 megakelvin. By focusing on the case with 1 megakelvin, we have performed also higher resolution runs, and we have came to some interesting conclusions. First of all, the case with 1 megakelvin base temperature exhibits extensive mode conversion inside the region where plasma beta is greater or equal to 1, which has an effect on the JZ current density, as shown in figure 2. By introducing anisotropic thermal conduction, we see that oscillatory reconnection is not killed, but instead persists. However, now it decays faster than it did before, and also there is a phase difference between these two cases, indicating that now we have a different oscillation frequency between the case with and without thermal conduction. Finally, in figure 3, I am showing you a profile for the temperature for each case used in the parameter study. These profiles can act as a proxy for the thermal pressure gradient, which is one of the restoring forces responsible for the oscillatory behavior in our system. Thank you very much for your attention, and I hope we can discuss in greater detail later on.